Let me very quickly introduce Stefan. So Stefan has a master's degree at ETH Zurich, where he focused on computational condensed matter physics. After his master's degree, he was fascinated by quantum machine learning and did a research internship at Cambridge Quantum Computing. And that led him to starting his PhD at his current position, where he's doing PhD at Institute of Science and Technology, Austria, trying to understand variational quantum algorithms. And he'll be talking about his recent work where they tried to avoid, or they tried to avoiding Barren Plateaus using classical shadows. So Stefan, please take it away.
So thank you very much for the invitation. So I'm looking forward to telling you about our work that we archived earlier this year and avoiding Barren Plateaus using classical shadows. So let's start off with a general overview of what I would like to talk about. So first, I want to give a brief introduction to what actually are Barren Plateaus, when do they occur, and a bit of a background of the research that has been done. Then I will tell you about the connection between Barren Plateaus and entanglement. And this will then lead to a brief overview of classical shadow tomography. And then as a last point, I will combine all of these ideas together and I will show you how to generally avoid Barren Plateaus using classical shadows. So let's start off with the introduction. So to set the stage, we're talking about variational quantum algorithms, where the main idea is basically you use the quantum computer to implement a variational wave function, which is used to approximate the solution to some computational problem. So this is a very generic approach. This could be you want to use, for example, a quantum machine learning where you want to classify data. This could be an optimization problem, or this also could be what we just heard, finding the ground state of a Hamiltonian of some quantum chemistry system. And so what you do is that you have a cost function which encodes the computational problem. And the goal is to find parameters that minimize this cost function. So essentially you're in some high dimensional parameter space and you're trying to find a low energy solution. So you're trying to walk down in energy to find a good local minimum, which then approximates the solution. And so what I will be focusing on today is the variational quantum eigensolver that we just heard about, where the cost function is an energy expectation value. So you have a Hamiltonian, which can encode some quantum chemistry problem or some condensed matter problem. And so what you do is the general approach is that you have some iterative procedure between a quantum computer and the classical computer, where the quantum computer is used to implement this variational ansätze. Then the qubits are measured. This gives you a bit string. And then the bit strings are taken to the classical computer, where you then use this information to compute the energy expectation value and the gradient. And you can then use the gradient information to update the parameters to go down in energy. And you do this as an iterative procedure between quantum computer and classical computer until you have converged. So now let's consider a general ansätze circuit. So this is here the hardware efficient ansätze circuit, where the idea is that you have single qubit rotational gates. So they rotate your qubits around the Bloch sphere. This can be in the X, Y, or Z axis. And the angle is a variational parameter, which is free to choose. And then the horizontal lines, they are entangling gates. And so you have this layered ansätze of qubit rotations and entangling gates, and you repeat this a few times. And so it turns out that for this ansätze and also a large class of ansätze, when you initialize your algorithm in this parameter space, most initializations end up in a region with vanishing gradients. And not only vanishing gradients, you also have an exponentially small gradient variance. So in this large parameter space, you're basically in a completely flat region most of the time. And one of the first works that explored this was from McLean back in 2018, where they analytically showed the scaling that in the Barren Plateau your gradient variance vanishes exponentially. And you can see this numerically here on the right, where they considered here on the x-axis the number of layers, so how many times you apply this structure, and then on the y-axis you have the gradient variance and as a log scale, and the different colors or different system sizes, you see this exponential decrease. And so if you are in a Barren Plateau, you cannot escape it efficiently by any means, because this requires you an exponential number of measurements to get this exponentially small value, so you're completely screwed when you are in one of those Barren Plateaus. So this problem has been around for some time, and there have been a number of different studies into this. So one of the famous ones is from Cerezo, who basically studied how the Barren Plateau problem depends on the cost function. So the cost function, basically you have a global, for a global cost function, so where you measure all qubits, you have some global observable. There the Barren Plateau occurs at circuit depth order 1. And if you have a local cost function, where you only measure a few qubits, so this is often the case in quantum machine learning, you do some classification, you only measure, let's say, 1 qubit. There you have local cost functions where basically there's a transition from trainable to a Barren Plateau, and a Barren Plateau occurs at around polynomial in system size depth. Then there has been a work that first alluded on this connection between entanglement and Barren Plateaus, but didn't fully capture the whole scope, and they particularly focused on neural networks here, right, quantum neural networks. So then a few months ago, there was this very nice work that was a theoretical investigation of whether what determines whether an ansatz has Barren Plateaus or not. And so this is a very, very nice theoretical framework where you can analytically figure out if a given ansatz has a Barren Plateau or not. But it doesn't tell you anything about how to avoid them, what is a good initialization, etc. So this is more of an abstract work. And so now I would like to kind of bring these things together and give an intuition of what's going on. So the first thing to note is that the Barren Plateau is basically caused by the randomness of the unitary that you apply. So basically, the unitary is so random that all information is lost, and also the gradient information. And if you measure the gradient, basically the information is just scrambled in Hilbert space, and it takes exponential resources to get the information back. And so this has been studied more mathematically. This is a known fact. And so what people say is that the unitary ensemble, so the different unitaries that you obtain when you choose different initializations, it needs to form a so-called T2 design for a Barren Plateau. So this just means that you match the Haar random ensemble up to the second moment. So basically you just have a bunch of random matrices. And so the randomness, in fact, can also be captured by the entanglement entropy that is present in the circuit. So let's go ahead and take here this hardware efficient circuit, and let's consider two system sizes, two subregions, or one subregion rho A prime. So A prime is now a small subregion, a few qubits, and rho A is going to be half of the system. And let's compute the second ring entanglement entropy. So this is a type of entanglement entropy for this. And let's see how this changes as you change the circuit depth. So on the top here, you see the typical plot of the gradient variance for different system sizes and this vanishing with that happens at a certain circuit depth. And now in the middle, you see the same thing for the entanglement entropy of half of the system with the rest. And you can clearly see that this really coincides with where also the gradient converges. And so basically the entanglement entropy, once it converges to its nearly maximum value, its page value, this indicates that you have encountered a Barren Plateau. And so if you now consider a smaller subregion, so this region A prime, which is a lot smaller, for this, it reaches page entanglement entropy as a smaller circuit depth. And we call this a weak Barren Plateau. So full Barren Plateau is if you check half of the system, and the weak Barren Plateau is if you check only a small subregion. And it will become clear later on why we do this. So in fact, you can analytically show and you can prove that if you have a two design, so this is two design and Barren Plateau are basically equivalent. In a two design, all the sub-regions will reach page entanglement entropy. So all sub-regions sizes that you check in a Barren Plateau will reach page entanglement entropy. And so we define a weak Barren Plateau as now a small sub-region reaching page entanglement entropy. So basically we have a small sub-region that is maximally entangled with the rest of the system. And so since for a Barren Plateau, all sub-regions have to reach page entropy, and also the large ones and also the small ones, a weak Barren Plateau is a necessary condition for a full Barren Plateau. You require that the small sub-region is entangled with the rest in order for there to be a full Barren Plateau. So if you avoid a weak Barren Plateau, you are also guaranteed to avoid a full Barren Plateau since you violate the necessary condition. So to make this mathematical talk a little bit more concrete, here's an illustration of a circuit. So you have these entangling layers, W. And so a weak Barren Plateau is now if there's a small subregion that is maximally entangled with the rest of the circuit. And then as you add entangling layers, the size of this region grows. And once this region has reached the full circuit, this is where a Barren Plateau occurs, a full Barren Plateau. And this coincides with the plot here in the bottom. Okay, so now equipped with this knowledge, we can understand one of the popular heuristics that are out there for avoiding Barren Plateaus into initialization. So this is the small angle initialization, where these single qubit rotation angles are now restricted to a smaller range controlled by this parameter epsilon. And so what this does is it simply slows down the growth of entanglement entropy that is taking place in the circuit. So if you look here at the numerics, the red curve on the top is the entanglement entropy for the full angle range. And on the bottom, this is the gradient variance. And you can see that very quickly after, let's say, 20 circuit layers, you are in the Barren Plateau, the gradients are exponentially small, etc. Now, if we restrict the angle range, the blue curve, the entanglement builds up a lot slower, and you can see that the gradient variance is well behaved here. It doesn't decay exponentially. And so if we go even smaller to this epsilon 0.05, the purple curve, the gradients are even larger. And so basically to avoid a Barren Plateau, you need to avoid page entanglement entropy, which is associated with a random state, with a random unitary. You just simply need to avoid that you encounter a random state in the Hilbert space. And so this condition needs to hold throughout the circuit optimization and not just in the beginning, which is very crucial. And so now this leads us to classical shadow tomography, because classical shadows allow us to efficiently check for weak Barren Plateaus during the optimization process. So now let's do a quick overview of shadow tomography. So let's say we want to estimate some energy expectation value. So some, let's say, quantum chemistry Hamiltonian, and we have M terms, M Pauli strings. And so depending on this Pauli string, we require a local basis transformation, because on the quantum computer, you measure in the Z basis. So if we encounter an X, Pauli X, or Pauli Y, we need to do a basis transformation. And so for every term, we need to do this. So basically this then means that in order to measure the full energy expectation value, we need to do roughly M number of measurements. It scales linearly in the terms. And then there's this 1 over epsilon squared, which is an additive error. So there's energy plus minus epsilon. So this is the scaling of the number of measurements. So in classical shadows, you do something different. In classical shadows, you instead you take your ansätze, your circuit, and you apply random single qubit Clifford gates. So basically, you just measure randomly in the X, Y, and Z basis the qubits. And you repeat this a bunch of times, and this allows you to build up a so-called classical shadow, which can be efficiently stored on a classical computer. And this classical shadow can then afterwards, once it's been obtained, be used to compute all sorts of observables that you want to get. And there's a rigorous performance guarantee for this procedure. And you can see that here now the number of measurements, the linear dependence in M has been traded for a logarithmic dependence. But now we got this shadow norm here, which depends on the locality of the operator. So depending on how many qubits you need to measure for your operators, this becomes inefficient. But if it is small, this is a very efficient procedure. So if you only need to measure a few qubits in your observable, then the classical shadow tomography is the best thing to do. And so to summarize again, the shadow protocol is highly efficient as long as the subregion is small and you're trading the logarithm M dependence with log M. And there are many VQA applications for this, where this is a natural choice, where you have this small support of the operator. And then also this offers a highly efficient technique for computing more complicated quantities, such as second-raney entanglement entropies. And so, in fact, you can then use the classical shadows to compute the second-raney entanglement entropies of all subregions containing k qubits. And the measurement budget scales as this equation shows here. And you can see that this is exponential in k. But for a weak Barren Plateau, we only need to measure a few qubits. And since a weak Barren Plateau is a necessary condition for a full Barren Plateau, if you avoid a weak Barren Plateau, you also avoid a full Barren Plateau. So then this offers a very efficient way of fully avoiding Barren Plateaus. And so now to bring all these ideas together, let me explain to you how to do it. So at first, you need to initialize outside of a Barren Plateau. So basically in this parameter landscape, most of the landscape is dominated by Barren Plateaus. And then there's a small subregion, which is Barren Plateau free. And you want to initialize in this Barren Plateau free region. This can be done with a variety of different things using small rotational angles. There's this famous identity block initialization where you basically have a unitary and then you undo it. So you just have an identity in the initialization. And there are many more, but they all work in the same way. They simply avoid a random state, a typical state, so they don't have page entanglement entropy. And so we now suggest to do the full VQA procedure using classical shadows. So basically you compute the shadow, you perform the shadow measurements. You then take the shadow and you compute your energy expectation value, your gradient, and the second-raney entanglement entropy of the subregions. And then you need to check if the second-raney entanglement entropy has reached the page value or not. If it has not, then you can simply continue on with your optimization. And if it has, then you need to fully restart the algorithm from the beginning. And the reason for the full restart is because if you have encountered a Barren Plateau, then you cannot escape it. So you must avoid it at all costs. So it's better to simply start over. And the reason why this learning rate plays a role here is that the learning rate controls the update magnitude. So you're in this Barren Plateau free subregion in parameter space, and you want to stay in this subregion. So if you have a large learning rate, you're quite likely to actually jump out of this region and go back into the Barren Plateau. And so the learning rate is linked to a larger potential change in the entanglement between the updates, and it needs to be controlled. And so what we did here is we looked at the purity change between updates for different learning rates. So in red here, you have learning rate 1. You can see that it's fairly large. So you're quite likely to jump out of this region. And as you go down with the learning rate, you are more and more controlled. And so you will more likely stay in this Barren Plateau free subregion. And so to wrap up the whole algorithm, we performed numerical simulations on the 1D Heisenberg model. So let's start at the top here in the red curve. This is now, we initialize outside of the Barren Plateau with these small angles, and we use a learning rate of 1. And you can immediately say that the entanglement entropy spikes up to the page value, so you immediately overshot the region and you're back in the Barren Plateau again. And you can see that the optimization does nothing. You simply stay in the Barren Plateau. Performance is very poor. So now we decrease the learning rate to a smaller value. This is now the blue curve. So you can see that the blue curve does avoid the Barren Plateau. It doesn't spike up to the page value. but the performance is still not very good. And the reason for this is because effectively you're trapped in local minimum and the learning rate is too large to converge. You're simply jumping around. And this can be seen by looking at the gradient norm, which is the bottom plot. So this is the blue curve. So if we now decrease the learning rate further, this is the purple curve where you can see that we fully avoid the Barren Plateau and we also get a very good optimization performance. And we nearly converge to the ground state energy. And so if we were to decrease the learning rate further, this is now the green curve, you can see that the performance is slightly worse. So the main message is that you basically just want as high of a learning rate as possible to still stay in this Barren Plateau free region in the parameter space. And so with this, I'm already at the end of the presentation. Thank you very much for your attention. And I would like to also thank my collaborators, in particular Ramel, who provided the theory support for this work.
Yeah, the few of us who are in the room, you get actual clap. But yeah, thank you again for the great talk. I think we have some time for questions. So if you have any questions, feel free to unmute yourself. And that's good.
Yeah, I think I have my camera has changed. So I think I have the only question yet. So I think it's clear that if you decrease your learning rate, that you go slower, right? And can you avoid that by reusing some of your high learning rate results to seed your low learning rate results, your low learning rate optimization? So reuse some of the initial points.
I'm not sure if I fully understand the question.
So there's some time with the high learning rates before you hit the Barren Plateaus, right?
Mm-hmm.
And this means that you go to like you improve your objective function there. So
yes.
you could reuse these values of the angles to
yes, certainly. So I mean, certainly the smartest thing would be to not, fully restart. But the problem is that if you have done your optimization and then you have encountered the Barren Plateau and you then go one step back, you're already very close to those random states. So it's not entirely clear how many steps you should go back, but for sure there is a better technique than to fully restart. So there for sure is a better thing to do, something adaptive.
And then that follows to my second question. So can you avoid falling into the Barren Plateau? So you say you get really close, but would it be possible to not get into it if you take 5 steps back or 10 or 100 and you switch to a lower learning rate? Are you guaranteed?
Yes.
Are you going
yes.
Down again, or is it?
Yes, I mean, this is basic. This is simply a. You're entirely right. This is what you can do and what you should probably do. You basically just you're in this Barren Plateau free region and you want to maneuver in it while staying in it, and you want to have a quite high learning rate to still have good optimization performance, right? Otherwise, you will get stuck in some poor quality local minima. So there's a trade-off between the two. But if you have encountered it, then you could for sure go back a few steps and start from there. But typically, you would usually encounter the Barren Plateau very much in the beginning of the optimization. So it's really about an uncontrolled step out of this region. And the magnitude of the step also really depends on the model. So we've also done simulations for different models. So it's not always that that learning rate 1 is fairly large, but it could also be learning rate 0.1 or 0.01. It really depends on the model.
Do you have any indication there? what it is that causes, like what it is that causes the radius of this page entropy, basically, like where you don't reach it.
I would say that in the parameter space, so I mean, if you have a different model, then also the gradient will be different, right? The gradient depends on the model that you use. So perhaps the gradient magnitude is different. The landscape itself is, well, I'm not sure.
It would be really good to have a heuristic on where to start with your learning rate, right? So.
Yeah, that's entirely true. But so far, like for the problems that we have checked, we simply just like try a few learning rates, and for these, so far we haven't encountered any issues.
Cool. Thank you.